Have you ever wondered if those big social programs we hear about, the ones designed to improve health or education, are actually working? How do we prove that the good things we see are because of the program and not just something else entirely? Well, today we're going to dive right into that. We're exploring the super clever, real-world methods researchers use to find out what really works.
So let's imagine a scenario. A school starts a free lunch program, and pretty soon, test scores start to climb. Awesome, right? But hold on. Was it really the food? Or maybe it was that amazing new teacher who also started that year. Or what if the whole local economy just got better and families were feeling less stressed? See the problem? To find the true impact, we've got to somehow separate the program's effect from all that other background noise of life.
And the secret to solving this puzzle is a really cool idea called the counterfactual. Seriously, this is the ultimate what-if scenario. To measure a program's real effect, we have to compare what did happen to people in the program with what would have happened to those exact same people if the program never existed. The big question is, how in the world do you measure something that, well, never actually happened?
Well, in a perfect, pristine lab setting, scientists have what they call a gold standard for creating that counterfactual. But as we're about to see, the real world is almost never that simple. This gold standard is the randomized controlled trial, or RCT. You've definitely heard about these from medical trials. The concept is beautifully simple. You take a big group of people, and then, basically by flipping a coin, you randomly assign some to get the program and others to a control group that doesn't. Because it's purely random, the two groups are, for all intents and purposes, identical. The only real difference between them is the program itself. But here's where reality bites. Ethically, can you really deny a kid a free school lunch just for the sake of an experiment? The answer is often a big, fat no. And beyond that, there are just massive practical and political roadblocks. You can't always just randomize people's lives. The real world is messy.
And that is exactly where our main topic for today comes into play. When that gold standard just isn't an option, we need a smarter, more flexible toolkit. So let's meet the quasi-experiment. And just to be clear, these aren't some sloppy second-best option. They are incredibly clever, practical ways to find real answers in our complex world.
So what's the big difference here? It all comes down to one thing: how people get into the groups. In a true experiment, an RCT, it's totally random. And we call the group that doesn't get the program a control group. In a quasi-experiment, it's non-random, so we call them a comparison group. Now that might just sound like a simple name change, but trust me, that one single distinction changes absolutely everything.
And that brings us to the single biggest hurdle. The second you give up that pure randomness, you run into this risk called selection bias. It's basically the fear that the two groups you're comparing weren't really the same to begin with. Maybe the people who signed up for the program are just more motivated, or they live in a slightly different area. If your groups aren't truly comparable from the get-go, you just can't trust the results. Figuring out how to deal with this is the whole game.
So how do researchers solve this puzzle? It's time to open up the Quasi-Experimental Toolkit and look at some of the really creative strategies they use to build a convincing comparison group, even without randomization. Okay, so researchers have some really smart tricks up their sleeves. First up, you've got the similar neighbor approach, where they literally find a nearly identical villager school next door to act as a comparison. Or they can create a statistical twin for every single person in the program by finding their perfect match in a dataset. Another really cool one is the cutoff point, where they compare people who just barely made it into a program with those who just barely missed the cutoff. And sometimes, the very best comparison group is the group itself, using a simple before and after look to see what changed. Now, once you have your two groups, the program group and the comparison group, there's this brilliant little piece of math to analyze the data called difference in differences. The logic is that stuff is always happening in the world, right? Stuff that affects both groups. So you don't just look at how much the program group changed. You also look at how much the comparison group changed during that same time. Then you find the difference between those two changes. Let me just walk you through this. Look at the table. First, you figure out the change for the program group. That's their after number minus their before number. Simple enough. That's your first difference. Then you do the exact same thing for the comparison group. After minus before. That's your second difference. And then, this is the magic part, you subtract that second difference from the first one. That process filters out all the other noise, and what you're left with is the true, isolated impact of the program. Pretty neat, right? All right, enough theory. Let's make this totally concrete. How does this actually work out in the field? Let's take a look at a real-world evaluation of the Mary's Meals school lunch program in Malawi. They had the exact problem we've been talking about. Everybody knows feeding kids is a good thing, but how do you prove it's making a measurable difference in their education? So they couldn't just randomly give food to some schools and not others. That wouldn't be right. So they used a quasi-experimental method. Specifically, they used that similar neighbor approach we just talked about, which is officially called a non-equivalent groups design. They found 10 schools that were getting the meals, and then they very, very carefully matched them with 10 super similar schools in a nearby district that didn't have the program yet.
So what did they find? The results were really powerful. By using that difference in differences math, they found that the program was causing real, significant, positive changes. They could say with confidence that the school lunches led to a lot less hunger in the classroom and a much better ability for students to concentrate. This is exactly the kind of credible, real-world evidence these methods give us.
Okay, so after all this, what's the final verdict on quasi-experiments? Well, they are incredibly powerful and useful tools. But, like any tool, you gotta know their strengths and weaknesses. They come with some important trade-offs.
On the plus side, they're practical, they're actually doable, and they are often way more ethical than a pure RCT. You can even use them to evaluate a program that's already up and running. But there's always that weakness. That risk of selection bias is always lurking, and you have to work really hard to minimize it. The stats can also get pretty complex, and while these methods tell you what changed, they don't always explain how or why it happened.
So here's the bottom line. Quasi-experiments are not perfect. They aren't a magic wand, but they are an absolutely essential and powerful tool for understanding what works. They give us a credible way to find answers in the messy, complicated, and definitely non-random world that we actually live in. And I'll just leave you with this final thought. Now that you get the logic behind all this, the next time you see a news story or a report that claims some program works, you're ready. You can ask the smartest question in the room. Okay, but who were they compared to? Thanks so much for tuning in.